Hello and welcome to session 6 of Unit 2. This session would introduce you to conservation of mass energy in nuclear chemistry. By the end of this session, you should be able to solve simple conservation of mass energy calculation problems. Let's begin by looking at some examples of problems. Question 1. In a nuclear reaction, mass decreases and energy increases. What about the laws of conservation of mass and conservation of energy? Are mass and energy not conserved in nuclear reactions? Do we need to throw out these laws when it comes to nuclear reactions? Now, the answer is simply no. All the laws still apply. Law of conservation of mass and conservation of energy still apply when it comes to nuclear reactions. The issue is that the masses are being converted to energies, and so the sum of mass and energy is always conserved in nuclear reactions. So it's more appropriate to say that the sum of mass and energy is always conserved. Question 2. The simplest compound nucleus is the deuterium, the nucleus of hydrogen 2. It consists of a proton and a neutron bound together by a strong nuclear force. The masses of these particles are proton 1.0073 U, neutron 1.0087 U, and deuterium 2.0136 U. A. Calculate the difference in mass between deuterium and one proton and one neutron. The question A is simply telling us that, so we are looking at the solution. The question A is simply telling us that we should calculate the difference in mass between the nucleus, deuterium, and the nucleon, that is, the components of the nucleus, which is the proton and the neutron. So, if we can put the mass of the nucleon together, then we subtract it from the mass of the atom or the nucleus. The mass of the nucleon, the proton and neutron, is given by this. So this is the mass, the sum of the mass of proton and neutron, and this is the mass of the nucleus, deuterium. So we subtract the sum of proton and neutron from the nucleus, and this gives us negative 0.0024 U. Now we know that 1 U is equivalent to 1.66 times 10 to the power negative 27 kilogram. So by converting from U, which is atomic mass unit, to kilogram, we multiply the change in mass by U, the value of U in kilogram, and this gives us negative 3.98 times 10 to the power negative 30 kilogram. Now, next question B says calculate the binding energy of deuterium in joules and in MeV. To address the question B, the binding energy we have learned that is given by change in energy. So change in energy, change in E, which is equivalent to mc square. So if that is the case, we already have our m, which is calculated in A, and the speed of light, which is 3 times 10 to the power 8, When we substitute these values into our equation, it will give us 3.58 times 10 to the power negative 13 joules. So this will be our binding energy. The question continued to say that we should calculate the binding energy in mega electron volts, that's MeV, mega electron volts. But every 1.6 times 10 to the power negative 19 joule is equivalent to 1 electrovolt, which means that 3.58 times 10 to the power negative 13 joules will be equivalent to what number of joules? What number of electrovolts? So that is the problem we need to solve. By dividing the binding energy in joules by 1.6 times 10 to the power negative 19, it will convert it to electrovolts. But the electrovolts here is multiplied by 10 to the power 6, which represents mega. And so our answer will be in mega electrovolts. So we'll end up having negative 2.2 mega electrovolts. The question C says that we should calculate the binding energy per nucleon of the deuterium. Now, to solve this problem, we know that the deuterium has 2 nucleons. So the binding energy per nucleon is given by the binding energy divided by 2. So we divide the binding energy we have calculated by 2, and by dividing it by 2, it will give us negative 1.1 mega electrovolts. So that is the binding energy for each nucleon. So the question D says that we should express the difference in mass as a percentage of the sum of the masses of proton and neutron. The difference in mass we have calculated to be 0.0024, and the sum of the masses of proton and neutron is given by 1.0073 plus 1.0087. So when we solve this and multiply it by 100%, it will convert the mass difference to percentage, and we are getting approximately 0.1%. Now let's look at questions under mass change in nuclear fission. The first question we'll look at is says a possible reaction for the nuclear fission of uranium-235 is the reaction given here. So we have uranium-235 that is bombarded with neutron to give us the antimony Sb and the niobium Nb plus 4 neutrons, and the masses of the particles have also been given to us in the question, and the mass of neutron has also been given to us. So in the next slide, we'll look at the questions we need to address under this preamble. So now the problem we have to solve is to show that the energy change per atom of uranium is about 200 mega electrovolts, and calculate change in mass. To do that, we need the mass of all the atoms before the reaction, that's mass of uranium plus the neutron, and that will give us 236.0526 U. And we also need the mass of the product after the reaction. So we need the mass of antimony, the mass of NB and then the mass of the neutron. So when we put that together, we will get 235.8616 U. Once we have achieved that, we subtract the mass after the reaction from the mass before the reaction. So we do this operation and we get 0.191 U as the difference in mass. So that is the mass defect. But the problem is we should find the change in energy. So to get the change in energy, we multiply the mass defect by the speed of light squared. Our mass defect or change in mass is in U. That's atomic mass unit. So we need to convert it to kilogram. And to do that, we multiply by 1.66 times 10 to the power negative 27. That will convert it to kilogram. Then we go ahead to multiply it by the speed of light squared, and that will give us the energy. But at the same time, we need to calculate our energy in mega electrovolts. So we will divide the resulting answer by 1.6 times 10 to the power negative 19 joule per electrovolt, and that will leave our answer in mega electrovolts. So when you do your calculations very well, you realize that you will get 178 mega electrovolts, which is almost 200 mega electrovolts. We are to also calculate the change in mass per mass. So change in mass of the reaction, we calculated it to be 0.001 U, and the mass of uranium is 236. So we divide the change in mass by the mass of the reactant, and we get approximately 0.1%. These are self-assessment questions which I would want you to go through them and try your hands on them.